Greetings and welcome to the Chemistry 222 lecture for Chapter 21, which is where we're going to take quite a drastic change, and instead of talking about electron chemistry, which is basically all of Chem 221 and all of Chem 223 and most of Chem 222, we're actually going to talk now about the chemistry of the nucleus, so the reactions that happen at the proton and neutron level, and it's quite different than the normal kind of chemistry we do. Because protons and neutrons are held in the nucleus so tightly, the energy required to make reactions at this level quite a few magnitudes higher generally than the regular electron chemistry. So nuclear chemistry is pretty cool. Lots of interesting things to check out. And without further ado, let's get into it. As a quick review from Chem 221, the atom, the model of the atom that's used right now, atoms are basically like small spheres. And most of the area of the atom is taken up by where the electrons, if you will, circle around. And we talked about in Chem 221 how they don't really circle. There's probabilities and orbitals and all that kind of stuff. But the important part is that the electrons take up most of the volume. And in the very, very center, more or less, of the atom is the nucleus, which is a very, very small volume. But in that volume, you actually have most of the mass. Most of the mass of the atom comes from protons and neutrons, and that's where they're stored in the nucleus. So you've got this hyper small little nucleus with almost all the mass. The density of the nucleus is way off the charts compared to anything we're used to in our regular world, electrons around the outside, et cetera, et cetera. Now, because those protons and neutrons are so tightly bound in that small amount of volume, the energy required to keep them there is fantastic. All right, it's way above the normal kind of energies we've been used to in Chemistry 221 and Chemistry 222. So the reactions we're going to look at are generally much higher in energy than the reactions we've seen so far for acids and bases and sodium reacting with metal, stuff like that. When you get down to the nuclear level, then man, the energies are quite different. So think about that in the back of your mind. Some of the heroes and the pioneers, if you will, of nuclear chemistry or the areas of the nucleus include, of course, my beloved Marie Curie, who we talked about in Chem 221. Her husband, Pierre, was also an explorer, and Henry Becquerel. Henry Becquerel was the one that coined the term radiation because there were rays emanating somehow from these samples, et cetera, et cetera. They didn't understand the power of the nucleus, and with power comes danger, and that caused some bad results. So like poor Marie Curie died of leukemia, stuff like that. But there is a lot of potential. Power is an interesting thing. In the wrong, attitude, it can do bad things, but in the right things, you can do some really cool things with it. So my goal in this chapter is also to let you know that there is a lot of really cool kind of potential for nuclear reactions. And there's yays and nays with everything, and we'll talk about those two as we go through this section. On the periodic table, another thing to review is that all periodic tables have at a minimum the atomic number, the symbol, and the atomic weight. Well, they'll have those three at a minimum if they're like a real science periodic table. If they're one of the ones that hangs in your shower as a shower curtain, maybe not. But anyway, I digress. The important part for us now is not if your periodic table on the shower curtain is legit or not, but what is important is I want to remind you what the atomic number means. And the atomic number gets the symbol Z, and Z represents the number of protons in the nucleus, all right? And that's really important. If you change the number of protons, you change the atom itself. So like aluminum right there has an atomic number 13, so that means 13 protons. If you take away one of those protons, the atomic number would become 12. And on the periodic table, number 12 is magnesium. So you change the protons, you change the element itself. Now you can take or add electrons to make them positive or negative ions, stuff like that, but you don't change the number of protons without actually changing the element itself. You can change the number of neutrons as well, and that creates isotopes, which we talked about in Chem 221. So as an example of a boron atom, boron always has 5 protons because that's the atomic number. And if you add 5 neutrons into the mix, then you have a mass number, which gets the symbol A mass number of 10. And the symbolism that's used sometimes for these things is shown right here. The upper left-hand corner is the mass number, the lower left-hand number is the atomic number, and the atomic number and the symbol, of course, go really well together. Now, if you had, instead of 5 neutrons, you had 6 neutrons in boron, you'd still have 5 protons plus 6 neutrons, you'd have a mass number of 11. So boron 11, which is also referenced right here, is just another isotope of boron, and you would write a boron 11 with a superscript 11 instead of 10. The atomic number is still 5, the symbol is still B, so this is how you would write different isotopes. So you change the number of electrons in an atom, you make it positive or negative ions. You change the number of neutrons, then you'd have a different isotope. But if you change the number of protons, then you actually change the element itself. Okay, so this is a question that's a quick review from Chem 221. It says copper can be found as 2 primary isotopes, copper 63 and copper 65. Notice that the little superscript is usually listed after the name, so copper 63 would be 63Cu, etc., etc. Anyway, which isotope is more abundant? And it lists the 2 isotopes and says more information is necessary. This is a good time to get out a periodic table. And again, the periodic table I recommend is at mhchem.org/per-tab. But honestly, for this question, you can use just about any periodic table you want to. And what you need to look at here, first of all, find copper on the periodic table, and it's number 29. So that means there's 29 protons in copper. But what the number you need is the other number, 63.546. And 63.546 is the molar mass of copper. So if you have 63.546 grams of copper, you have a mole of copper. But if you remember back from Chem 221, that number is a statistical average of the isotopes of copper. And so in this problem, for example, you can literally write like a type of a number line. And I'm going to make a very cheesy one here. And again, I apologize because I am not an artist. But anyway, I wrote up there 63 and 65. And of course, that corresponds to the 63 copper and the 65 copper. Now, on a number line, halfway would be 64. And how this all works out is I'm going to look at that periodic table number again for copper, and it was 63.546. So roughly, all right, I'm going to make a little dashed line right there. Roughly, and again, my line isn't even straight. It's very embarrassing. So anyway, 63.546 would be roughly halfway between 63 and 64. The molar mass gives you a hint as to which isotope is most abundant, because remembering that the 2 isotopes together equal the molar mass on the periodic table, you can kind of see what's happening. For example, if you had 50% copper 63 and 50% copper 65, then the average of those 2 would be halfway between 63 and 65, which would be 64. All right. So if the number on the periodic table was 64, then you'd say you had 50% 63 and 50% 65. But again, the number on the periodic table there is 63.546. All right, that's a terrible 3. Anyway, 63.546. And 63.546 is certainly closer to 63 than it is to 65. And that must mean then that copper 63 is more abundant. And in Chem 221, we did a problem where we actually calculated the percentages. And if I recall correctly, copper 63 was about 70% of all copper, and copper 65 was about 30%. You can look these numbers up on Google to see that that's about what it is, all right? But the important part is that the molar mass gave you a hint as to which was the more abundant isotope. And in this case, it's certainly copper 63. In this section, because the energies are so much higher when we're talking about the nucleus, we're going to run into some special particles, quote unquote. One of these technically isn't a particle, but the other ones certainly are. And these are going to be very unique to nuclear chemistry. They're things we really haven't had to talk about, at least in this context, up until this point. So these are going to be things that are going to pop up in the upcoming lecture, so just get ready. The first of them is nothing more technically than a helium nucleus. Now, notice the symbol, especially on the left-hand side right there. If you have helium, then you have an atomic number 2, and the dominant isotope of helium is helium-4. If you look on the periodic table for helium, the molar mass 4.003, that's really, really close to 4. So you would think at first, if you wrote this normally, 4,2 helium like that, it would be regular helium, the kind of helium where if you're at a birthday party, you can open the balloon and then you talk like a chipmunk. But of course, I've never done that before. Okay, really, I have. But anyway, I digress. Normal helium is one thing. All right, it's cool for doing balloons, and you can use super cold things with liquid helium. This is not that kind of helium. We're talking in this thing about an alpha particle, and you can imagine this is helium on steroids. It like can't stop. It's super high energy. If you were to like have a balloon of alpha particles, and that'd be scary by the way, but if you did and you sucked them up like that, you'd be dead, because alpha particles we're going to see are super high energy. They're very reactive, and in your body they would cause a lot of damage. So an alpha particle, really is just a helium. All right, technically the alpha particle probably doesn't have any electrons because it's so high energy it pushes the electrons away. So you've got this super positively charged helium nucleus. This is pretty powerful stuff. The helium nucleus is seen as both regular 4,2 helium, but sometimes you're also going to see that symbol right there, and that's a Greek alpha, all right? So the alpha particle is like this supercharged helium. An alpha particle is oftentimes the product of some of these nuclear reactions, and we'll see it. So again, this is not, the normal birthday helium. This is something to be really careful with. You want to make sure you've got protection if you're around alpha radiation. Similarly to the alpha, there is a beta radiation. Now, normal electrons, we've seen, make chlorine chloride, or they turn the sodium metal into sodium ion, stuff like that. Well, beta particles are like supercharged electrons, and these are also things that you certainly don't want to be messing around with. Lots and lots of energy. Electrons are reactive as they are, so when you make them a beta particle, woohoo, they are super, super powerful. Now, the symbolism, which is going to be helpful to us later on, you can see right there. It's a 0 minus 1 E or a 0 minus 1 beta. That symbol on the right is a beta representing beta particles. This is kind of interesting. Remember in the type of system we're looking at, the lower left-hand number is number of protons, and the upper left-hand number is protons plus neutrons. When it comes to beta particles, these supercharged electrons, the 0 makes sense because there's no protons or no neutrons. The negative one is a little weird, so bear with me for right now. I'll make sense of this for you here in a little bit. So a beta particle has a 0 minus 1 E or 0 minus 1 beta. Either one is fine. The next one is a gamma ray, and really this isn't a particle, so that's why I made the kind of silly comment earlier, how they're not really radioactive particles. But anyway, gamma is literally gamma radiation. It's pure energy. It's the highest energy found on the electromagnetic spectrum. We talked briefly about gamma radiation in Chem 221. We're going to formalize it. Gamma rays have the little symbol right there, gamma, all right, and that's just like pure energy. Gamma radiation is quite common in these nuclear reactions because there's so much energy. And if energy is released, a lot of times it's gamma. You can also have X-rays, though. X-rays are also common in nuclear reactions, but gamma radiation is the one that's seen most often and the one we'll focus on. Now, in addition to all of these, once in a while, we're going to talk about protons in this section. And a proton can be listed as 1,1p, like the example on the left. And again, that makes sense. Lower left-hand number of protons, which of course is 1. Upper left-hand number, protons plus neutrons, which of course 1 plus 0 is 1, no problem. One proton is also going to be often symbolized as 11H, a hydrogen atom, all right? Because the hydrogen atoms are going to be the protons and stuff, and good to go. In addition to protons, neutrons will also be useful. A symbol for a neutron is 10N. And again, no protons, so that's where the 0 comes from. 1 proton plus neutron in the upper left. Neutron is the symbol, no problem. So protons and neutrons are kind of cool. But the newest one, and the one that really gets me jazzed up here as your Star Trek loving instructor, is a positron. A positron is an anti-electron, all right? So first of all, just look at the symbolism. 0 plus 1 E or 0 plus 1 beta, all right? The regular electron, 0 minus 1 E or 0 minus 1 beta. So they're very similar. There's a reason why the one is -1 and the other one is +1. An anti-electron is not a proton, which also is +1 in the lower part there. So that's why there's a 0. So anyway, these are going to be players. We're going to talk about all of them in more detail, and there is a nuclear chemistry guide in the companion and online that might help you when you go through this section. Let's talk about the anti-electron a little bit more. An anti-electron, which is also known as a positron, is an example of antimatter. Now, if you have been interested in science fiction, antimatter is something that's used quite often. And in Star Trek, my beloved Star Trek, antimatter is what was used to basically fuel the warp engine so they could go long distances and stuff with an antimatter-matter conversion. That's really cool, but actually antimatter is a real substance. So in the upper part of this picture, there's regular matter, a regular hydrogen atom. And normally a regular hydrogen atom would have an electron and a proton. And if you look at the quarks inside, and this is an example of elementary particles, which is a special kind of physics, there's different kinds of quarks inside there, and you can see the little symbols and the colors. Well, antimatter, you would literally have anti-hydrogen atoms. And instead of the electron, you'd have a positron, because a positron is an anti-electron. And instead of a proton, you'd have an antiproton. And you can see inside there, there's anti-quarks in the antiproton, making up the anti-hydrogen atom. Whoa. So the theory is, especially if you start dipping into science fiction, is that there could be an exact copy of you, but an antimatter version. And the antimatter version in an antimatter world would have no problems. But if you, the matter version, and your antimatter version of you came together, touching matter and antimatter usually creates a lot of energy. And we'll talk about that here in a little bit. But one thing I do want to point out is that the positron is a true example of antimatter. It's an anti-electron. And positrons are somewhat common anyway, in this nuclear chemistry field.
You're aware that radioactive materials give off energy, especially if we expose this sample to ultraviolet light. We can see it glow. There are 3 different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation. Here we have a nuclear scaler that measures radioactive decay. Each click that you hear is a nucleus of an atom that is decaying by giving off a radioactive particle. This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler. What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection. Let's place a beta particle in our sampler. We notice that there's a slight increase in the counts. The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. we notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample. We notice immediately that more energy comes from the gamma. 1 sheet of lead and 2 and even 3 that quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles, alpha and beta. Gamma is an electromagnetic energy wave. Well, let's see what happens as we go from being close to a radioactive source to far away. We notice that the amount of radioactivity is greatly decreased by distance.
This is a pretty cool video, and it shows especially beta and gamma radiation and how it's detected. And they're using a Geiger counter, which is that kind of tube thing there, and the tube has like a detector. It faces the radiation, and each one of the clicks is essentially a radioactive particle interacting with the Geiger counter. So if you have a Geiger counter with those clicks going off, then you know that you've got radiation around. Beta and gamma, as well as alpha, have different properties. Alpha, we saw, was essentially a helium nucleus, so it has mass. It's also the heaviest. Beta is an electron. It has mass, but it has less mass than alpha, so it's maybe a little bit better. Gamma, on the other hand, is pure energy. It's like shining a flashlight, if you will. There's no mass at all. So you can stop alpha and beta radiation pretty well. Like alpha radiation generally is stopped by your clothes, and beta radiation needs something a little bit better, but it's usually by skin, all right? Gamma, on the other hand, is much more difficult to stop. They saw there how the beta radiation was stopped pretty well with lead. Gamma, though, it took a little extra there to kind of kick that down. Distance is another factor, too. If someone was to point one of these radioactive sources at me, intentionally or unintentionally, sometimes the best thing to do literally is just run, because the farther you run, then the more chance the radiation has to interact with something in the air or a wall or whatever, more likely to be stopped. So anyway, it's pretty interesting. We'll talk more about Geiger counters later on, but you can see there are different kinds of radiation, and depending on what kind of radiation you have, there's different ways to stop it. The first thing we're going to look at in this chapter is how to balance a nuclear reaction. And they're not too hard to balance, all right? I find them kind of fun, but again, you know, I'm a chemist and I like Star Trek, so make your own conclusions. However, the punchline of balancing a nuclear reaction is that the number of reactant protons has to equal the number of product protons. And the same thing for the neutrons. The number of reactant neutrons must equal the number of product neutrons. All right, so this is kind of interesting. It's kind of like law of mass action, but with a little bit of twist, as we'll see. So here's an example of a balanced nuclear reaction. This is a reaction between a radium isotope. It's radium-226 on the left-hand side. And if you look on the periodic table, radium is number 88. Well, radium-226 decomposes into an alpha particle, which is 4,2 helium. You could have written that as 4,2 alpha. That would have been fine. In addition to the alpha particle, it's also a radon emitter. It's a radon-222. If you look on the periodic table, radon, symbol Rn, is number 86. Anyway, this is a balanced reaction because the lower left-hand numbers, which are the proton numbers, are 88 equals 2 plus 86. All right, no problem. And the upper numbers, which are mass numbers, which are technically protons plus neutrons, but that's a way to confirm that the neutrons are the same on both sides. So 226 on the left equals 4 plus 222. If those numbers for both mass numbers and atomic numbers are balanced, you have a balanced nuclear reaction. So this is a kind of problem you might see. Uranium-235 is the active component of uranium samples. And a lot of times when people wish to make nuclear power or nuclear bombs, they want the uranium-235, not the more abundant uranium-238. But anyway, uranium-235 decomposes through beta decay to a new product. Let's find the identity of the new product. All right. Now, beta decay just means that a beta particle is emitted. And since uranium has 92 protons and it's uranium-235, you can write the symbol like that. So uranium-92 on the bottom lower left, 235 in the upper left. If you have, as I said, a beta decay, that means that a beta particle is going to be a product. And this is something we'll see. If you see that something is decaying or is undergoing an emission, whatever is decaying or undergoing the emission will be a product. So these would be beta decay reactions or a beta emission reaction, same thing. It just means that a beta particle is going to be a product. And if you look back on that list, beta particle is like the supercharged electron. It has a 0 - 1 e. And yes, you could write 0 - 1 beta, and that would be fantastic. So in this problem, we don't know what the mystery product is, this thing right here. But we can figure that out easily by remembering that protons have to equal each other on both sides, and the mass numbers, which means neutrons, must also equal each other on both sides. So you can probably see the math isn't too crazy here. The top part, 235 equals 0 plus A. You can solve for A. On the bottom part, 92 equals -1 plus Z, and you can solve for Z. So let's do the easiest one. 235 equals 0 plus A, so that's no-brainer. A, 235. Woohoo! The bottom one, 92 equals -1 plus Z. So Z equals 92 plus 1. Put the -1 on the other side. Z is 93. So you put this all together and look on the periodic table to see that Z93 is Neptunium, Np. So the balance reaction here, uranium-235 on the left, a beta particle on the right, plus Neptunium-235. All right, so no big deal. A periodic table, of course, will be helpful. If you don't know that 93 is Neptunium, which is quite all right, you can absolutely look that kind of stuff up to figure it out. The inner reaction here is worth talking about. Inside the uranium-235, what's really happening is a neutron is breaking down into a beta particle plus a proton. And you can see now maybe why beta particles are listed as they are. Beta particles 0 - 1 e plus a proton, which has the symbol 1,1p. You can see that on the right, you've got 1 and 0 on the top, so you'd have a 1 on the left. And on the bottom right, you've got -1 plus 1. That goes to 0. That's a 0. So a neutron in uranium-235 is breaking down to a beta particle plus a proton. It makes your uranium go to Neptunium. It's going up in atomic number, even though the mass number stays the same. And that's kind of a fascinating thing. Neptunium has one more proton, but technically one less neutron than uranium-235 does. This is something that's kind of interesting. A lot of these nuclear reactions, the neutrons will break down into an electron plus a proton. If you remember from Chem 221, we said that the neutron was the most massive of the three particles. Protons were close, but a little less, and electrons were really small. Well, a proton plus an electron essentially equals the mass of a neutron, and the +1 proton and the -1 electron will combine to make something neutral. Whoa. Anyway, this area is pretty trippy, as you can probably see. Here's another reaction. We've got a uranium-235 on the left. This time it's breaking down to a thorium-231 plus a mystery particle. Well, the question is, what is the unknown particle? And again, what you can do is use the fact that the protons have to equal each other on both sides, and the neutron/mass numbers must also equal each other on both sides. So let's do the Z of the mystery particle first. 92 equals 90 plus Z. So subtract 90 from both sides. You're going to see that Z here is a 2. And let's do the mass numbers now. On the top, 235 equals 231 plus A. So subtract 231 from both sides. You're going to see that A there is 4. And if you remember from the list of particles before, something with a 4 and a 2, well, automatically the 2 would mean that you'd have a helium for X, or you could write, of course, alpha. 4, 2 is the symbol for alpha. So let me get rid of my little funky stuff there. There we go. Now you can see clearly without my graffiti that yes, we do have an alpha particle, which has the symbol 4,2 helium or 4,2 alpha. All right. So again, knowing what those names mean in terms of a formula there will be helpful as you go through it. This one, you have to know that 4,2 helium is an alpha particle, et cetera, et cetera. Emission and decay, like we talked about earlier, imply that something is being created, i.e. it's a product particle, and there's quite a few examples of this when it comes to these reactions. This is an example of a positron emission. Now, positron has the symbol 0 plus 1 beta or 0 plus 1 e, either way is fine. So because it's a product, we would say this positron is being emitted, or you could say it's a positron decay. Either one is fine. This is a polonium-207 undergoing positron emission to a bismuth-207 nucleus, which is kind of interesting. Sometimes you'll hear the term capture, and just like emission and decay imply a product particle, capture implies that something is a reactant. And a real common example of this is what they refer to as neutron capture. So in a neutron capture reaction, there's going to be a neutron as a reactant. The neutron is 10N, so this is an example of a fluorine-19 undergoing neutron capture to become fluorine-20. And again, you can figure out what the missing particle is because reactant protons equal product protons, and reactant mass numbers equal product mass numbers, et cetera, et cetera. You'll see different kinds of particles and decays and emissions and captures and stuff, but just remember capture means reactant, while decay or emission means that that missing piece is going to be a product. Now, positrons and antimatter are really interesting. Paul Dirac was the one who, in Chem 221, we talked about briefly. He took relativity and applied it to quantum mechanics, so the m sub s spin quantum number popped out. But anyway, he was actually the first one to predict that antimatter could be a real substance, and it was 1928. And the antimatter is identical to regular matter, except it has like the opposite charge. So down here in yellow is an example of a positron reaction when it reacts with an electron. And anytime you have matter with antimatter, in this case it would be an electron with an anti-electron, you can see what happens. The lower left-hand numbers cancel out and go to 0, and the upper left-hand values also cancel out and go to 0. So in this case, a positron and an and a regular electron, they just combine to make gamma rays. This is called an annihilation reaction because the matter is totally turned into energy. We'll talk about that more later. If you have two particles coming together, you create two gamma rays. There's different kinds of rules and this level that while number of particles equal number of rays, don't worry about that. But this is actually something that's very useful. So in addition to sci-fi geeks like myself getting all excited here, this annihilation reaction is actually used in what's called positron emission tomography, PET, and that's a medical facility that's used, for example, at OHSU, stuff like that. Lots of examples of annihilation reactions. This is an example of what's a neutrino and an antineutrino coming together. And again, those are also types of these subatomic particles. We won't talk about those as much, but anyway, they do come together, creating gamma radiation. Pretty crazy. Neutrino was also something that was first postulated by Pauli. Pauli exclusion principle was another thing from Chem 221, where every electron has its own set of 4 quantum numbers. He was the one that predicted the neutrino, and neutrino detection is an active area of research even today. These radioactive isotopes will often decay through alpha particles or beta emissions or once in a while neutron captures. But anyway, they have like a pattern that they follow. And in this case, this is what they call the decay scheme for uranium-238. And knowing now what you know about nuclear particles, you can kind of see what's happening. So let's focus on the first uranium-238 to thorium-234 right there. Well, 238 minus 234, that's 4. And on the bottom, 92 minus 90, that's 2. That's going to be an alpha emission. So going from 238 to 234, that's an alpha emission. If the atomic number decreases in this scheme, you can see that it's always, it's basically 2 atomic units. So there's a thorium-90 to radium-88. That's 2 units. That's going to be another alpha decay. But you also see sometimes where the atomic number is increasing. So like there's a thorium increase here and another increase there to uranium. Those will be beta emissions because in a beta emission, a neutron is turned into a beta particle, which is kicked out, plus a proton, so the protons are going up. So every time you go, the arrows go down and to the left, it's alpha decay. Every time the arrows go to the right, it's beta decay. At the very bottom of the scheme is a lead. A lot of times lead, especially the lower 200s of lead, are seen as kind of the end point of these reactions. It's not necessarily the higher mass number, so like lead-214 isn't as stable, but lead-206 is pretty stable. If you look at the periodic table for lead, which is number 82, the mass number is 207. So around 207, i.e. in this case 206, that's the end. That's when the atom is stable and it won't undergo further decompositions. So it's kind of cool. So all the radioactive elements either do or could have a scheme like this, and it'll show where they start. It'll go through different kinds of decays, maybe than even what we're seeing, but eventually there will be an ending point where it's considered stable. There's also what they call a metastable nuclei. In a normal atom, if electrons are excited, all right, they can relax and they'll emit like ultraviolet, infrared, visible radiation, stuff like that. So electrons will create types of energy bursts that come out once they relax back to their ground state. Well, nuclei, where the protons and neutrons are, can also be excited. So the nucleus starts like bouncing around more, or you can think about the protons and neutrons aren't as separated as they were. Anyway, after a while, these nuclei will also relax back down, but when they relax, the energy released is orders of magnitude higher than when electrons relax. So while electrons relax, they create visible light, ultraviolet, etc., etc. If the nucleus relaxes, it creates a gamma ray. This is an example of a technetium sample which has been excited to a metastable state. And if you look at the yellow part on the left, there's a little M right there. And that just means that technetium has been excited to a more high energy state. And like all high energy states, they eventually relax. So when it relaxes down to regular technetium, which is what that is, a gamma ray is kicked out. All right. So the metastable technetium is being relaxed to a regular technetium, and also a gamma ray is kicked out. If you see an M in a little picture like that, or a little diagram description of an atom, that just means it's in this excited metastable state. And all you have to do to balance a reaction like that is just write the element without the M plus a gamma ray. And there's lots of examples of this, and a lot of the heavier elements can be excited and then released with a gamma ray. It can be really helpful. Metastable nuclei can be used in a lot of medical imaging processes, and I'll show you a video of this later. Technetium-99m is definitely used a lot at a lot of medical places like OHSU in Oregon, and we'll talk about this more later. So again, this stuff is pretty wild at first, but there are actually a lot of practical uses for it that allow scientists and doctors and engineers, etc., to get some really cool information on things that would be difficult to know otherwise. Because the nucleus has so much energy inside it, and it's creating gamma rays and et cetera, and the neutrons are decomposing to protons, et cetera, we really should have an overview of the forces of nature. And there are 4 forces that dictate how things stick together when you look at the universe. And we're going to be dipping our toe a little bit in physics here, but not too much. So just kind of hang on a little bit. So the 4 forces that determine how everything in the whole universe sticks together, the first one that's probably already familiar to you is gravity, or the gravitational force, all right? And gravity is a relatively weak force, all right, believe it or not. It's a very long-range force, so it keeps the Earth circling around the sun, and it keeps our solar system in the Milky Way galaxy and things like that. It keeps you from floating away on the Earth, which is, of course, kind of neat to know. However, compared to the other forces we're going to look at here, it is considered to be a relatively weak force. So like we have talked about gravity a little bit, like with gas pressure, it pulls the mercury back down the column as the atmospheric pressure pushes it up, kind of thing. But it's not one that's as strong as the other ones. But gravity is important. I'm not dissing gravity by any means. There's a force called the weak nuclear force, and in physics, this becomes really important. This is also a relatively short-range force, and it does create beta decay, all right? So when a beta particle is emitted, when a neutron breaks down, this is actually supposedly the result of the weak nuclear force. It's kind of beyond this course to talk more about the weak nuclear force, but it is one of the 4 forces. It's not so important to what we're going to talk about here, but I would be remiss if I didn't include it, just like not talking about gravity. So there it is. The 2 forces, though, that are most important to us here in chemistry, the first one we've talked about a lot. And the first one is the good old electromagnetic force. All right, this is also called Coulombic forces, electrostatic forces. This is the good old positive, negative charges we've been talking about since Chem 221. Electromagnetic forces are pretty long-range forces, all right? They do keep the electrons around the nucleus. So the positive nucleus is attracted to the negative electrons and vice versa. And this is the force that keeps that happening. People that know more about forces than I do have compared the electromagnetic force to gravity, and they claim that electromagnetic force is 10 to the 36 times more powerful than gravity, all right? So that's a pretty good number, and I'm not in a position to debate it, but electromagnetic forces are certainly important for us in chemistry. They keep electrons around the nucleus, all right? Once one electron goes away or comes in, stuff like that, that's also electromagnetic. So pretty powerful force, all right? But the problem with electromagnetic force is in the nucleus, because in electromagnetics, opposites attract, so negatives are attracted to protons, but also remember, like forces repel. So negative electrons get too close to each other, they repel, and certainly positive protons next to each other will repel. And if you have a nucleus with a super small volume, that means those protons are being kept to each other in a very tight area, in a very small force. Now, electromagnetic force doesn't like the protons being close to each other. So thankfully for us, there's a 4th force, and it's called the strong nuclear force. And again, the same people that said that electromagnetic forces were 10 to the 36 times stronger than gravity, people feel that the strong nuclear force is about 1,000,000 or 10 to the 6 times more powerful than electromagnetic forces. The strong nuclear force keeps the protons next to each other, all right? It's very, very short in the range. It's like 10 to the minus 15th meters. That's a femtometer. But it is more powerful enough to overcome positive repulsions, all right? So the reason that protons can be next to each other in the nucleus is not because of electromagnetic forces. It's the strong nuclear force. And so as long as the strong nuclear force is capable of overcoming the positive repulsion, no problem. You can think about the strong nuclear force as the glue that holds the nucleus together. Without the strong nuclear force, I would argue that atoms, except for hydrogen, couldn't form because you couldn't have two protons next to each other. They would repel like crazy, starting with helium. Hydrogen would be okay, but nothing past hydrogen. So the strong nuclear force allows basically all the elements, I would argue, from helium on to be together. But it is very short range. So we'll come back to that and how that affects nuclear stability in a little bit. Some atoms are very, very stable. All right. For example, carbon, oxygen, stuff like that. In a nuclear context, anyway, they're very stable. So the question is, why do nuclei sometimes become unstable? Like, why is plutonium so unstable? Or why is it so difficult to create some of the heavier elements? All right. And the idea is that nuclei become unstable generally because the electromagnetic force, the positives, negatives, begin to overpower the short-range, strong nuclear force. That strong nuclear force is very, very small in the duration, how far it works, all right? And so once you get past 10 to the minus 15th meters, which is not difficult even for very small protons and neutrons, then the strong force breaks down and you start to have proton-proton repulsion. Positive forces start kicking out. Now, a little bit of magnetic dilution, which is what they call, does help to make the nuclei more stable. So as you add neutrons, if you will, get between protons. The protons are further from each other and the electromagnetic repulsion is less. So sometimes magnetic dilution, which just means adding more neutrons, will make a nuclei more stable. But even magnetic dilution coupled with the strong nuclear force only works to a point. And after a while, you get to the point where all nuclei are considered unstable. So as a general rule of thumb, and there are exceptions to this, generally speaking, elements up to calcium, and calcium has a Z atomic number of 20, the most stable nuclei generally occur when the protons and the neutrons are equal to each other. So if you look at calcium, the molar mass of calcium on the periodic table, my periodic table says 40.078. That's close to 40. So that means if calcium has 20 protons, that most stable nuclei of calcium must also have 20 neutrons. 20 protons plus 20 neutrons would be a mass number of about 40, and that's what we see on the periodic table. But this doesn't exist universally. So for example, helium-3 and hydrogen-1 are both fairly stable, and those don't have protons equal to neutrons, all right? The main one of helium is helium-4, which does have 2 protons and 2 neutrons, but helium-3 does have some uses, and that's, of course, not equal protons and neutrons. Past calcium, but up to lead, then generally speaking, the most stable nuclei have more neutrons than protons, all right? So if you look at, let's say iron, all right? Iron is number 26, and the mass of iron on the periodic table, molar mass, 55.845, which is pretty close to 56. So 56 minus 26, that's 30. That indicates that the most stable isotope of iron probably has 30 neutrons relative to the 26 protons. So past calcium up to lead, there should be more neutrons than there are protons. But past lead, you can argue that all isotopes are unstable and radioactive. All right, so everything from bismuth on, arguably, is unstable. Now, there's discussions about this. Some people think that some of the bismuth isotopes and even some of the uranium isotopes are stable at a certain level. But this is controversial, and some people think they do break down even then. So for our purposes, let's consider everything basically past lead as unstable and eventually will undergo some kind of radioactive decay. So this is kind of interesting how the number of neutrons can help indicate if an atom is stable or not. If you had an atom past calcium but before lead, which had an even number of protons and neutrons, it would be fair enough to state that probably that's not going to be stable. It's going to decay. But if you have more neutrons than protons, then it can happen, stuff like that. So scientists that study nuclear chemistry a lot have created graphs which look something like this. There's different variations of them, but this graph has number of neutrons on the y-axis and number of protons on the x-axis. And if you look at that kind of colored part in the middle there, there's a lot of dots, and there's black dots, and they're surrounded by red dots. The black dots represent the stable nuclei, the ones that scientists don't feel are going to break down. The red dots represent isotopes of the atoms which are unstable. They will undergo some kind of radioactive decay. Now, there's a line right there, which is where the protons and neutrons are equal to each other. The slope would be 1. So you can see that from about calcium, which would be about 20, from about 0 or more likely 1 for hydrogen up to calcium, then generally speaking, that black line is pretty accurate relative to the black dots. But you can also see then that past number 20, past calcium, the black dots tend to slope up. So you're ending up with more neutrons than you have protons. So the more stable black dot nuclei do have more neutrons than they have protons, which is kind of interesting. Scientists have termed this black dots in the middle and red dots on the outside as a peninsula of stability inside a sea of instability. So use your creative mind here a little bit. The black dots would be the peninsula of stability. Those are the stable atoms, the stable isotopes. But outside of that, you have the red dots, the sea of instability. And that's kind of cool. And remembering that eventually you're going to get to the point where there are supposedly no more stable nuclei than the little red dots here. I'll try and add in some just because I feel artistic, I guess. I don't know. The red dots would continue on and on and on. So the peninsula of stability and a sea of instability is a term that's used a lot of times to represent stable nuclei and how this all works. Now, generally, the unstable nuclei that are above the stable line undergo beta emission, all right? So if you have too many neutrons, then you start to undergo beta emission. The neutron breaks down into a proton and an electron. On the other hand, you have alpha emission over on this side when you don't have enough neutrons relative to protons. And then the lower ones, a lot of times, will undergo positron emission or electron capture. So you can kind of make general trends, and of course they're not all inclusive, there are many exceptions, but generally speaking, that's how these different isotopes are going to react. So the unstable ones will do this. If I can use your creative license just a little bit longer, some of the scientists that are studying or have studied nuclear reactivity and nuclear stability have proposed something which I just can't help but talk about, and it's called the island of stability. So Glenn Seaborg, we're going to see later on with a video, he was one of the most influential chemists in this area of all time, and one of his graduate students was Ken Moody, and Ken Moody is still creating different kind of things. Anyway, they proposed that beyond the sea of instability, you might have islands of stability. And this is a really interesting concept. So there's an instability kind of zone and it keeps on going and stuff like that. However, there's been proposals, theoretical proposals, where maybe if you get up to like mass numbers of 184 and stuff like that, or even beyond, you might start seeing stable isotopes, all right? And these stable isotopes would be things like carbon or magnesium that you could weigh out and they wouldn't break down to nuclear things. This is very theoretical. I love the imagery. We definitely have a peninsula of stability in a sea of instability, but it's very cool to think about, at least as a chemist anyway, that you might have somewhere out there islands of stability where you'd have heavier atoms which are stable and you could make cool things with them. This is a proposal. It's not by any means confirmed. If you're interested, here's a link to a PBS show that talked more about it. Pretty exciting stuff. This graph kind of shows what was happening before and the different kinds of reactivity that's possible. So on the x-axis, again, you have the number of protons, and on the y-axis, you have the number of neutrons. And then as the atoms become too rich in neutrons, you begin to have the neutrons decay through beta decay or beta emission. If there's not enough neutrons, then you sometimes go through alpha decay, and then the lower ones will a lot of times undergo electron capture or positron emission. So it's kind of based on number of neutrons and stuff, if they're neutron poor or neutron rich. It's just kind of a general trend and stuff that people see. Beta decay will occur in isotopes with a high neutron to proton ratio. So one example of this we've seen already is uranium-235. It breaks down to a beta particle, 0-1e or 0-1 beta, and that neptunium-235. So this is one possible decay scheme for uranium-235. You can also have positron emission or electron capture if the electron's on the reactant side. Those generally occur for low neutron to proton ratios. Now, this is an example of a nitrogen-13 isotope. Nitrogen is usually nitrogen-14. You can look on the periodic table for nitrogen. The molar mass is about 14 grams per mole. So 13 would have a low neutron to proton ratio. It doesn't have the 7 neutrons that nitrogen-14 has, all right? Anyway, generally speaking, those will result in positron emissions or they'll undergo electron capture. You end up then with a different kind of isotope. Nitrogen-13 would create carbon-13 and a positron. Then you also have the alpha decay, and generally speaking, the heavier ones by default will go this, but it's not all the time the case. This is a radium-226 example we saw that breaks down to an alpha particle and radon-222. So there's no way that in this class I would say, well, which is more likely, beta decay or alpha decay, but you can kind of hopefully see how this stuff works, and there are some trends that you can make when you study this extensively.